Hello, hello. Okay, so before we start, were there any problems on the homework that you guys want me to go
Is there
over?
any speakers? Oh, you need them.
Are there any problems that you need explaining on the homework? No? Okay. Okay, so guys, make sure you have graphing calculator on hand, something that can do sine, cosine, and tangent. Yeah. Yes, we're gonna need that for today. Is everyone okay with the audio, with the video? Okay, so were there any problems on the homework that you guys will want me to go over before we start this week's stuff? No? So everything was fine then? Okay. Okay, so someone asked me to go over the graphs. So if you see on the homework, something like problem 3, or maybe I think a better example is problem number 8. So for the graphs, well, how do we find displacement from a velocity over time graph? Does anyone have any ideas?
The area.
Yeah, it's the area under the graph. But why is that so? Well, velocity times time equals displacement, right? So that means it must be the area under the graph. Okay, so if there were any confusion with the graphs, that's how you would do that. So someone asked me about how to get time. Maybe I'll wait just a little longer for people to come in. I'm just gonna get started now. Okay. So I'm gonna share my screen. Just wait a second. Okay, can everyone see the PowerPoint? Is everything okay with the PowerPoint? Anyone see it?
Yeah.
Okay, good. So week two. Week two is two-dimensional kinematics. So last week we were doing motion in one dimension, but this week we're doing stuff in two dimensions because when things move, they're not always going in strictly one direction, okay? So topics. We're gonna first review our kinematic formulas because those are really important. And then we're gonna talk about vector addition and then projectile motion. Okay, so projectile motion is basically when I throw a ball into the air and it goes some distance, just like how you would do that in soccer, football, all those things. Okay. So first, let's review the kinematic formulas. Okay. But I'm not going to go over the obvious ones. So I'm just going to review the ones that we're going to use most in two-dimensional kinematics, which are displacement equals initial velocity times time plus 1/2 at. Okay. And then the other one is v squared equals v0 squared plus 2 at. So these formulas, you should get pretty familiar with these since we're going to use these a lot in two-dimensional kinematics. Okay, vector addition. So, as I said last class, velocity is a vector. And in day-to-day life, we're going to have lots of vectors on an object. For example, next week when we're going to do forces, we can sometimes have a bunch of forces being applied on an object. We have to add those forces together. So we got to talk about vector addition. Okay, so last class we only talked about vectors in one dimension. They're all on the same line. Okay, but now our vectors can go at an angle, something like in the xy plane, right? Okay, so the important thing to know is that every vector has an x component and a y component. What do I mean? This vector has an x component here and a y component here. Okay, so every single vector in two dimensions, we can divide that into an x component and a y component. Let's label that vx, vy, then we have the vector over there. Okay, so we can consider these vectors as the sides of a triangle, right? And we have a right angle right here. So the way we can relate the x components and y components of a vector to itself is the Pythagorean theorem, right? We take the legs of the triangle. Okay, so this is the equation relating the x and y components of a vector to the vector itself. This is basically the Pythagorean theorem, and I don't think you will have that much trouble remembering this one. Okay, so how do we add vectors? Okay, so if I had a vector, let me first clear all this first. If I have a vector of, I don't know, magnitude 8, okay, and I had another one of magnitude 10, okay, well, can I just add them together to have a vector of magnitude 18? Well, no, not necessarily, because the magnitude 10 vector could go at an angle, right? And the important thing to remember is that we can only add vectors when they're going in the same line, when they're going in the same direction, okay? So if they were like this on the same line, then we could add them to make 18. But if it's anything else, if it's at an angle, then we can't just directly add the magnitudes. So we can only add vectors when they're going in the same direction. So I'll draw my xy plane here. What if I had my 8 vector going at here at this angle, and I had my 10 vector going at a different angle? Well, how would I add these? How would I get them to be on the same in the same direction? Well, I can't actually change themselves, but I can divide each into their x and y components, right? So I have a y component here, x component here. I have another y component, and another x component. 10, x8, y8, 10. Okay, so now, as you can see, the y vectors are in the same direction. You can just add them together. And the x components are also in the same direction. So then if we add all of these together, then we will have the x and y components of our sum vector, the final vector, the sum of these two vectors, okay? So that is how we add vectors. We have to first divide them into their x and y components, and then we add their x and y components to make our new vector, which is the sum. Okay, so let me give you an example here. If I have a vector of 8 going at 50 degrees to the vertical, 50 degrees to the vertical, okay? And a vector of 10 going at 20 degrees to the vertical. What is their sum? What is the sum of these two vectors in magnitude and direction? Well, the first thing we can do is find the x and y components of these two vectors. Let's start with 10. Okay, so we're going to have to make a right triangle here, right? Well, it doesn't seem like we can use the Pythagorean theorem here. So what will we do? Well, as we can see in a right triangle, we have the relationship SO, CA, TOA, right? This is the definitions of sine, cosine, and tangent, right? So if I wanted to find the y component of this vector of 10, well then the sine of 20, by definition, that's the opposite over the hypotenuse. Y10 over 10, right? So then if we multiply 10 on both sides, we get 10 sine of 20 is the y component of the 10 vector, right? And we can do the similar thing with the x component here. If we use the trigonometry again, we can see that 10 cosine 20 is 10. Is everyone with me here? Are there any questions? No questions? Okay. So now we have the x components and y components of the 10 vector. Now we just need to do the 8. So if we make a right triangle here, we have the x component and the y component. And what I like to do is I like to change, I don't really want a 50 here to the vertical. Instead, I would like to think of that as a 40 degree to the horizontal, okay? Because that makes my life a lot easier. And that basically changes my x components. Clear up a little bit, it's getting messy. Okay, so I can use the same thing. 8 sine 40 is the y, and 8 cosine 40 is the x, right? And now we can just add the x and the y together of each, right? So we're going to add 10 sine 20 to 8 sine 40, and we're going to, let's first do that. So I'm going to get out my calculator, sine of 20 times 10. Now we add that to 8 times the sine of 40. So if my calculator is not wrong, I have 8.56 as my x component, my final vector, the sum. Maybe I'll label that x sum. Okay. Now I just need to add the y components. Oh wait, that was the y component. Sorry, this is the y component. Now we need to add the x components. 10 times the cosine of 20, adding to 8 times the cosine of 40. And the x component is 15.53, my x sum. Okay, clear up this work here. My final vector, just erase this. Final vector is going to have an x component of 15.53 and a y component of 8.56. right? And for the magnitude of this vector, I will just use the Pythagorean theorem. I will square both of these. And take the square root. So my final vector has a magnitude of 17.73. Okay, but how do I find the angle it has? Because every vector needs to have a magnitude and direction. Well, if we see this angle, the tangent of this angle theta is the opposite over the adjacent, right? So, take the opposite, divide that by the adjacent. And so, if we use the inverse tangent function, and on your calculator, that should be the button if you press second and then the tangent button. Okay, if we take the inverse tan on both sides, then we're going to have theta equal to, let me just plug that into my calculator, 28.86 degrees. Okay, does anyone have any questions about how I did this vector addition? No questions? Alrighty, that's good. So now we know velocity is a vector, okay? So what if I had a velocity in the xy plane going like this? Right, we're gonna have, as we know, we're gonna have a vx, actually a vy, and a vx, right? Well, what does this actually mean? Well, this means that while this object is moving in a velocity this way, it's simultaneously moving in the x direction at vx and moving in the y direction as on vy. Okay, so this is what it actually means. When an object is moving at an angle like this, it's both moving in the x direction at a speed of vx, and it's moving in the y direction at a speed of vy. Okay, but first let's generalize what vx and vy are in terms of the angle theta here. Well, as we know, we have, and how will we relate that to the velocity? Well, the angle, the sine of the angle, is the opposite vy. So v sine theta is vy. So this is the y component of our velocity, okay? So this is something you should be able to figure out intuitively, but it's always easier to remember this. And what is the x component? The cosine of theta is vx over v. So v cosine theta is the x component. All right? Does everyone have this down? Are there any questions?
I'm still writing.
No? Okay. Well, how do we prove the other relationship that we could make, that vx squared plus vy squared equals v squared, right? Because this is the right triangle. How can we prove this? Well, if we plug these values in as vx and vy into our equation, we're going to have v squared sine theta squared plus v squared cosine squared theta. Does everyone know how I did this? I just plugged v cosine theta in and v sine theta in as vy. Okay? So I can divide all the way through by v squared. We're going to have sine squared theta plus cosine squared theta equal to 1. Okay? And this is a common relationship that we all know, right? Sine squared of theta plus the cosine squared of theta is equal to 1. So this is how we prove how all these relationships match together in the end. Now we have projectile motion. So what is projectile motion? Let's just say I'm kicking a football at 40 degrees and the ball is going it's gonna, by intuition, it's gonna go in a curve like this, right? Well, as I'm kicking the football, it has a certain vy, it has a certain vx, right? We know that vy is v sine 40, and Vx is V cosine 40. And the really important thing to remember here is that at any point on the projectile's path, let's just say it might be here, its velocity is going to be tangent to the curve that it takes. Okay? And so we can divide any point on this curve, its velocity, to a Vx and a Vy. Okay? And the important thing to remember here is that in any projectile, its x component of velocity, it has nothing to do with its y component of velocity. Okay? So we can do our calculations and everything like that separately in terms of Vx and Vy. It doesn't matter what Vx is, it doesn't change what Vy could be, okay? Anything that goes on in the y direction has nothing to do with the x direction, okay? So what if I asked you, how long is this ball going to be in the air? Well, obviously it's going to fly, and then it's going to hit the ground, right? So what does this mean? Well, this means that I have a Vy up, right? That's propelling my ball upward, which will give it time in the air. And it's going to come up and come down, right? So we don't really care about Vx because Vx doesn't really depend, Vx doesn't affect when my ball will hit the ground, right? Because that's the vertical aspect of the ball's motion, okay? So the cool thing is that if I have a maximum height h, and I were to throw a ball vertically up, and it will still have that same h, then it would be the same, it would take the same amount of time for the ball to go up and come down. This is purely because of the fact that only the y component of velocity has effect on when the ball will hit the ground. Okay, is everyone with me? Okay, so if I wanted to find out how much time it would take for this ball to hit the ground, then I would just use my formula, displacement equals v0t plus 1/2 at squared. The first thing I need to do is I need to find my positives and negatives. I'll find my positive up here, my negative down here. My displacement is going to go up, it's going to hit the ground 0. Okay? What is my v0? My v0 is my vy, because my vertical component of velocity, that's the only thing affecting the amount of time that my ball is going to be in the air, right? Because horizontally, there's no obstruction that the ball is going to hit that will stop it, right? It's going to fall until the ball hits the ground, and that depends on the vertical motion, right? So in this equation, it's going to be Vy. And then we have 1/2. Remember, our gravitational constant G is going to be negative in this case, right? Because my negative is downward, and gravity always pulls downward, t squared. Okay, so now if I were to solve this, I can get rid of these t's. So basically Vy is the amount of time it's in the air. Okay? Is there any questions that you guys have? Okay, so the amount of time that an object is actually in the air only depends on its y component of velocity. So just as using what I just said, the x component is free to it's independent from the y component as well. Okay, so if I'm going, so let's just analyze what's going to happen on the x dimension. Okay, well, is there any acceleration in the x dimension? Well, in physics, well,
No.
you can think, well, there could be wind, right? But in these kinds of problems, we're going to neglect wind. So if there's no acceleration on the x component of velocity, then it's going to stay constant, right? Because if there's no acceleration, there will be no change in velocity. So the important thing to know is that Vx does not change. So it stays constant throughout the entire projectile path. Okay, so what if I asked you, how far would this go in terms of horizontal distance? Well, Vx is going to keep going to the right, right? The ball is going to keep going to the right until it hits the ground. So it's going to depend on the time here, right? because as long as the ball is in the air, then Vx will be applied, and it's going to be going at the Vx in the x direction. So, to generalize this, basically we'll just take the Vx, multiply the amount of time that the ball will be in the air. So that's how far this ball is going to go. In this case, I've already solved for what g is. So it's just Vx times 2 Vy over g. Okay? So this is projectile motion. The two key things to take from this is that that the y component and the x components are completely independent, and that the amount of time that the ball is in the air only depends on the y component. And how far the ball goes, well, it depends on the amount of time it's in the air and its x component of velocity. Okay? Are there any questions? No? Okay. Good. Now we have some problems. Yay, we can practice what we've learned. So let's first start with vector addition. Here's a problem for you guys. And I'll give you some time to figure this one out. So if you are having some problems, having some trouble visualizing this, I highly advise you to draw out a graph on the XY plane, and that's going to help a lot. For now, I'm not going to be answering personal. Maybe I will. I'll give you maybe one or two more minutes. Okay, so just a survey here. How much more time do you guys think you need? 4 minutes? Maybe I'll go until 8:30 and then I'll explain the problem. I don't think we have a few years or even a whole lifetime here. We only have 30 minutes left. Okay, so I'm just going to go ahead and explain these. So the important thing we have to do first is draw out our diagram of the x and y, okay? So we have one vector pointing at negative 80 degrees. It looks something like this. And it's going to go at 16. And then another pointing at 60 degrees, positive, also 16. What is the total acceleration on this object? So what this means is that I have to add these two vectors together. So, but first, why acceleration? Would acceleration change anything? Do I need to know anything special about acceleration? Well, no, as long as these things are vectors, then all the basics of vector addition will apply. Similarly, it's not going to change. So basically, first we're going to divide these into our x and y components because I can't just add these right now directly, right? I can't just add 16 and 16 to get 32. They have to be pointing in the same direction. So I'm going to divide it by x and y components. So what is my y component here? Well, I know that's 16 times the sine of 60. Okay, so this is I'm just going to draw a dot here. I know that's my y component up. And what is my x component here? Well, that is 16 times the cosine of 60. Okay? So what about the 80? Well, I know it's going to be pointing down, right? So I'm going to have a downward acceleration of 16 sine of 80, but I'm still going to have something going to the right at 16 cosine 80. Okay, so now I have all my x and y vectors out. So now I can just add them, right? Now, because they're in the same direction. So I'm going to first add my x components. 16. Well, I'm going to add cosine of 80 plus the cosine of 60, all by 16. I think that is 10.78, right? And then now we're going to do our y, right? So first, this one is going to go up, but the other one, the other vector, is going to be going down. So it's going to be subtracting from this one. So I'm going to do 16 sine of 60 minus 16 sine of 80. So I'm going to do sine 60 minus sine 80 times 16. So in the end, I'm going to have negative 1.9. So what does that mean? My y component of my sum is going to go down at 1.9, and my x component to the right at 10.78. Okay. I think I did that right. So now, this is just a right triangle. I'm going to move this vector to here so it's more clear. I didn't change the magnitude or direction, right? So I can move these vectors wherever I want to make a right triangle, as long as I don't change their magnitude or direction. So now for the magnitude, I'm going to use the Pythagorean theorem. Okay, so 10.78 squared, adding to 1.9 squared, take the square root, 10.95. That is my magnitude. So what is my angle theta? Well, we're going to use the right triangle to see how tangent theta is 1.9 over 10.78. So I'm going to use the inverse tan sides. And if you don't know where that is you press second and then you press the tangent button. So I'm going to take the inverse tangent of 1.9 divided by 10.78. Theta is almost exactly 10 degrees. Well, it's quite a bit far off, but I'm going to round like that. Okay, so it's going to be actually negative 10 degrees because it's going down. Okay, are there any questions on how I did that? Nope. Okay, then velocity as a vector. Okay, so give you a few seconds, not a few seconds, a few minutes to do these. Actually, don't do the first one. I want to focus on the second one here. So let's just don't do the first one. Just do the second one. Because we don't have that much time available for us. I see Sharia is there explaining trigonometry to those who don't know them. Thank you to Sharia.
Which way is the boat propelling itself?
What?
Which way is the boat propelling itself?
Well, it's just going to go across the river. So let's just say it's going to go forward like this. Okay, sorry.
Oh,
The river is here. This is like a bird's eye view down on the river.
yeah.
Okay, and then, so the river is going to be pulling it this way. Okay.
That makes sense.
How much time do you guys think you need? Because I need to get to the projectile motion because you're going to see that a lot more than you're going to see questions like these. So how much more time? I can estimate 1 or 2 minutes. Okay, I'll do 1 minute and then I'll explain it. Okay, so I'm just going to explain this now. So if we look at these, so the boat is going forward at, what is that, 17, I think? And then the water is pushing it to the right at 20. So this looks a lot like the x and y components of the boat's overall velocity, right? So we can just use the Pythagorean theorem here to find its overall velocity. That's just 17 squared plus 20 squared, square root of that. So I'm just going to do that right now. 17 squared plus
26.25.
Okay, thank you. That is 26.25. So that is its velocity, 26.25 meters a second. So what is the angle? Well, if we have this angle here, theta, then we can see how in the right triangle, tangent theta, 17 over 20. Take the inverse tan on both sides. And we can see how inverse tangent, 17 over 20, theta is 40.36 degrees. Okay? Are there any questions on how I did that? No? Okay. Yay, projectile motion. I'll give you maybe 3 minutes to do this one. Let's go for 4 minutes. So this problem is basically saying how this ball is going to go up, it's going to land. So how far is this displacement in terms of its velocity and the angle theta? If you don't get this question, it's totally okay, because these are one of the more difficult questions. It's just important that you put some thought into it at least, and at least try to figure this one out. If you don't, that is totally fine. The important part is the mindset of trying to figure out something like this. Okay, if you didn't get it, that is totally fine, but I'm just going to explain it now. Okay, so as we know from the example I gave a while back, we know that the x component of velocity doesn't change, and and the amount of distance it goes depends on the amount of time it's in the air. So I'm just going to label that as t, and when that's multiplied by the x component, that gives us our distance, the displacement. Okay. So how do we find time here? Well, let's first turn this into Vy and Vx. All right. So we can see how only the vertical component of velocity is responsible for calculating how long this object is in the air. Okay, so now I'm going to define positive as up, negative as down, and since it starts on the ground and ends on the ground, so the displacement is 0, its initial velocity is Vy, and that's being added to 1/2 times negative g t squared. Okay, does everyone follow how I did that? Okay, so now if I divide through by t to make things simpler, then I get rid of these, okay? So now if I move Vy to the other side, I get negative Vy equals negative 1/2 gt. So Vy, 2Vy over g is equal to time, okay? Does everyone see how I did that there? Now we can just plug this guy in as t, and in the end we're going to have 2 times Vy times Vx over g to equal to the distance displacement. Does anyone have any questions about how that works? Okay, but we can't stop here yet because the problem wants us to make it in terms of its actual velocity and the angle theta. So we can turn Vy into V sine theta and turn Vx into V cosine theta. Plugging these in, we're going to have 2V squared sine theta cosine theta over g. Okay, does everyone see that happening? Now we can simplify it even further by using the trigonometric relationship of 2 times the sine of theta cosine theta. All this is equal to the sine of 2 theta. Okay, this is a pretty important trigonometric relationship, but in physics you're not going to use it that much, but in math later on this is going to be important. Okay, so we can simplify this even further. Turn all this, let me just clear up my space here, into v squared sine of 2 theta over g. This is the displacement, the horizontal distance, okay? And the important thing to note about this formula, this range formula here, is that this only works if the object lands in the position in which it was launched. So it's got to land at the same height as if it was launched. Okay, if this were to land on like a table here, then this formula is not going to be valid. Okay, so an important thing to note here is that you can only use this formula if the object starts and ends in the same height. Okay, so this is basically a shortcut to finding the distance an object goes. And this is not totally necessary for finding the range of an object, but this is very, very helpful. Okay, so now using the answer from the last problem, what angle should a projectile be thrown to maximize distance traveled? Okay, so this is going to depend on the angle, right? So somehow we're going to want to maximize sine of 2 theta. If we go back to our unit circle, right here, the sine of theta is maximized here at 90 degrees. So that means 2 theta must equal 90. Dividing through gets theta equals 45 degrees. Okay, so this is the max. If we launch an object at 45 degrees, this will be the maximum range that we can obtain. Okay. Now let's do this problem here. So there are two ways to do this. You could use the range formula, which is a really good shortcut for you, or you could just solve it according to separately according to the y and x components of velocity. Okay, and if you want to use the range formula, I'll just write it again. Displacement b squared sine of 2 theta. Okay. Someone wants me to turn back a page. So, is there anything that you need to turn back? So, if you don't catch fully on the stuff I'm going to talk about, you can always watch the replay of today's lesson on YouTube later, and it's gonna be on my YouTube channel. Okay, so make sure to subscribe for more, because I know.
How tall is little Johnny?
Okay, so for this one, I'm just gonna assume that little Johnny throws from the ground, because little Johnny is a small kid. Okay, so it's like neglectable. His height is neglectable according to the amount of distance. So I'm just gonna assume that he starts on the ground and ends
So
up.
is he
Okay. So it's not gonna
the
have.
ground?
Yep, he's 0 centimeters tall. Yes, we're gonna just
Oh.
assume that's the case here. Although even if he was like a little taller, like the height of a 2-year-old, then his height is not going to be that much to affect our answer here. So our answer is still going to be pretty accurate, if you could say that. So with the range formula, I don't think this should take that long. So let me give you guys 1 more minute. Or do you guys need a little more time? Yeah, I'm just gonna go for 1 more minute. Then I'll just explain it then. Okay, I'm going to explain this now. One way you could do this is if you just solved for the x and y components separately, but we're just going to use the range formula for simplicity's sake. Okay, so he wants the object to go at a range of 10 meters. So d equals 10. We know that gravity is 9.8, and his v is 10. Okay, so we have everything in our equation that we need except for theta, and that's what we're going to solve. Okay, so 10 equals 100 sine of 2 theta. 9.8. Is everyone following this? Okay, so 98 equals 100 sine of 2 theta. So what we're going to have here is that 0.98 equals sine of 2 theta. Taking the inverse sine of both sides. Okay, that is the second button time, and then you press on the sine button. So if I take the inverse sine of 9.8, 0.98 actually, we're going to get sine of, actually, 2 theta, 78.52. But we need to notice here how if we just plug this into our calculators, it's not going to give me all the solutions that this equation has. Okay? Because if we look on the unit circle again, just going to look at the positives here. If we have, let's just say we have our sine theta, that we have the sine. Remember how the sine is the y value, right? If I have a sine like this, I could have 2 solutions here, this angle and this angle, right? And the formula here is that the other angle that we need to have here is 180 minus theta, okay? And you can visualize this if I were to draw this diagram. a little more skewed. Like if I were to take it like this, if they were to be like this, right? So we can see how 180 minus theta would give me my second solution. So I'm going to do 180 minus that. The other solution for 2 theta is 101.48. Okay, so now I divide both of these by 2 to get my final answer. So one of them is going to be 50.74, and the other one's going to be, let me just do that real quick. The other one's going to be 39.26. So if we visualize this, what is this going to look like as a projectile? Well, so on one of the occasions, he's going to throw lower, right? So it's going to go something like this. It's going to hit the vase. Oh no, terrible drawing. And then it's going to go higher. You see, guys? Do you guys see that happening? Right? So this is how we can have 2 solutions for theta. Okay, so I think we only have time left to do these 2 problems. Okay, so give you a few minutes to do these. So for the first problem, this is initial velocity.
This is horizontal projectile motion, right? So initial.
So this ball is basically on a building. It's being thrown parallel to the ground initially, right?
Oh,
but we know that's going to take a path something like this,
yeah.
where it's going to land 24 meters away. Okay?
Wait, are we trying to find the initial x velocity or y velocity?
Just the initial velocity. So if you think about it here, if we're throwing it horizontally, is it going to have any y velocity? It's being thrown horizontally initially. It's just going to go in the x direction, right? At that instant.
Yeah.
So initial velocity is basically just the x velocity.
Oh, okay.
So right now we have 3 minutes left of class. Do you guys want to spend more time doing these? And that's going to extend class by a little bit, or should I just explain them right now? Which one would you prefer?
I'd prefer more time.
Working more?
Yeah.
Okay. You guys a little more time. And that means it's gonna class is gonna be extended just a little bit. I see Fiona has raised her hand. Do you have a question?
Oh, no, sorry.
Okay. That's okay. So how much more time do you guys think you need? Maybe I'll go for, no, that depends. I want to make sure I give you guys enough time to put at least some thought into these problems. We'll go for 1 or 2 more minutes. Is that okay?
I think it's fine.
Okay. So maybe 2 more minutes. Okay, so if you're not quite done with the second one yet, maybe I'll just do the first one right now. So this ball is going to be thrown and it's going to fall on the ground, right? So once it hits the ground, its motion is going to stop. Okay, so eventually we're going to want to find Vx, right? Because when the ball is being thrown horizontally, it has no vertical component of velocity. So whatever its Vx is here, that's going to contribute to the amount of horizontal displacement we're going to have. And the amount of time it's airborne times our our horizontal velocity is going to equal to our horizontal displacement. So eventually, we're going to have to find the amount of time this ball is going to be airborne, and then we're going to plug that into our equation and find our horizontal velocity. Okay, so how long is this ball going to be airborne? Well, if we remember what I talked about earlier, only the vertical component of velocity, or like the kinematics in the vertical direction, contribute to how long this object is airborne. So I'm going to use the formula d equals v0t a t squared. Okay, so I'm going to establish the positive as down and the negative as up. Okay, so its displacement is 45. And what is our v0? Well, that's going to be our vy, right? It's our initial vertical component of velocity. Well, since we're going horizontally, then that value must be 0. And this whole term goes away. Okay, so what about A? A is gravity, right? And gravity is pulling things down. And in this case, since I've set the positive as down, then gravity is going to be positive. So 1/2 times 9.8 t squared. So now I just need to solve for t. 45 times 2 divided by 9.8. square root. T is going to be 3.03 seconds. Okay, so now we have this T. We can plug this into our equation. Vx equals 24 over 3.03. And I'll just do that. 7.92 meters a second. Okay. Now for the second one. A football is kicked at 18 meters a second at an angle of 35 degrees to the horizontal. How long does it take for it to land on the ground? Well, just like in the first problem, the only factor contributing to how long the ball is airborne is its vertical component of velocity, right? So it's going to be going at 18 at an angle of 35, right? So now we just need to analyze how long it's airborne, right? And that gives us the equation d equals v0t plus 1/2 at squared, right? So we only really need to analyze the vertical component of velocity. We don't even need to analyze anything on the horizontal plane. Okay, so what is Vy? That is 18 times the sine of 35, right? And I'm just going to find what that is. So Vy is 10.32. Okay, so the vertical motion of this object is just like one that is thrown straight up at 10.32 meters a second. Okay, so in terms of vertical motion, these two situations are identical. Okay, so now I'm going to establish the positive is up, negative is down. My displacement is going to be 0 because it's going to start and land on the same place. And my V0 is my Vy, 10.32 times the time. And that is being added to 1/2 times negative g, because gravity is pulling things down, and I've established that downwards is negative times squared. And I'm going to divide through by t to cancel these. So my overall t is going to be 10.32 times 2 divided by 9.8. And just doing that on my calculator, 2.11 seconds. Okay. Are there any questions on how that works? No? I do have some more problems, but I'll probably just put that in the homework for this week. Okay?
Where do we
Well,
find
first
the
to review.
homework?
What?
Where do we find the homework?
Well, I'm just going to send the homework to you guys after class. Okay? And just to review all the things that we need to know. So first, adding vectors. So if we have 2 or more vectors, it doesn't matter how many vectors we have, as long as we divide into x and y components, then add. Then we're going to have our sum of our vectors. Okay? And then projectile motion. The x, or any motion in the x direction, is independent from any motion in the vertical direction. Okay, so we can treat those situations as separate, but the amount of time it's airborne depends on our vertical, and how far it goes in terms of this horizontal displacement is based on our horizontal initial velocity. And we note that this horizontal Vx will stay constant, okay, because there's no acceleration in the x direction for most of our problems. Okay, and the range formula again. Just a shortcut, if you will, for an object that starts on the ground and lands on the ground. Okay, if you want to memorize this, go ahead. I think it's a pretty good shortcut that's worth time remembering, but you could always solve for horizontal displacement by dividing our velocity into horizontal and vertical components. Okay, so are there any questions about what we talked about today? No? Okay, perfect. Stop sharing, and that is it. The video of our lesson, if you want to look over it again, it's going to be on YouTube. and I'm gonna send out the homework tomorrow. Bye, guys.
Hi.
See you next
Hi.
time.
Hi,
Yeah.
colleague.
Bye.
Can I?
Nice teaching.
Thank you. Yeah. Do you have a
Oh
question?
yeah. So I'm a parent. I actually have a few questions. If you don't mind, like have a stay
Yeah,
on a
that's
few
fine.
minutes.
Yeah. Uh-huh.
So because we signed up just from a link that a friend shared, so wanted to ask, like, this class is meant for like the grade range, and what is the objective you think the kids trying to get, like, at the end of the class? So that's one question.
Yeah. Well, the basics, it doesn't really matter how old the kid is. You just need to know the basic knowledge of trigonometry, as we talked today about sine, cosine, tangent, all those things, and algebra. Like, if you want, like, with the equations we have, you need to have a knowledge of algebra to solve those. So those are basically the only two requirements I have. And yeah, prerequisites. And if the student is in a lower grade but also knows those things, then they'll be fine in this class. It really just doesn't matter how old they are, just if they know how to do these things. Yeah, and in the end of this class, I'm planning to teach mechanics, which is basically just like kinematics, and we're going to talk about force next class, and then rotational motion and gravity and all those stuff. And I just really want these kids to learn, even if they're not in school right now. And I know that kids have trouble learning online, and I think it's really important that I start this class to give them a boost when their education may be, like, their status of education or the quality of education may be lowered. So that's basically my goal in this class.
Oh, and also, is it possible to, because it's a little hard for my son to catch up some of the things. Is it falling? Is it possible to send over some of the, like, the problem beforehand, or some of the concept beforehand, just so that we can do some pre-work and make the best use of your class? Because I sense he's hiding under the desk, but he has some or she has some, like, challenges in catching up. I think if we could have the opportunity to do a bit of, like, pre-work or go over some of the basic concepts as we scan through, I think it'll be more like, how do I say it? Like, easier for him, and to make the best use of the time.
I think that if you were to go to Khan Academy, do you know what that is? Khan Academy. So maybe I'll type it in the chat.
Oh yeah.
Khan Academy.
That's what I used.
Yeah, Khan Academy. It's completely free.
I know that. Yeah.
And if he goes and if she learns the trigonometry course on Khan Academy, so trigonometry, okay, and learns up to algebra 2, then I think she would be okay. So if she were to learn these two things, trigonometry in Khan Academy and algebra 2, that should be enough to do well in this class.
She's in the process of studying algebra. Sorry. I was just teasing him because he's hiding under the desk, so I caught it.
Okay, yeah. I see someone put in the physics.
Of, like, studying.
Yeah, the physics on Khan Academy. I tried that before. They only have videos in there and not a lot of practice problems. So yeah.
Do you have recommended, like, reference books?
I used it to help me for 1D motion.
So any physics book would work. It just there are physics books on varying difficulty, but the things I'm going to teach in this class are mainly non-calculus. There's not going to be any calculus in this class. So any non-calculus physics book would be enough. Yeah.
Okay. Oh, one last question. Did you maybe we missed it. Did you create a, like, Google Classroom kind of thing that we need to join, or it's just all through email?
No, I don't have a Google Classroom. I'm just gonna send all the worksheets and stuff through email. Yeah.
Okay. Show respect. Say hi to colleagues.
Hello.
Hello.
Yeah, this is she. Okay.
Okay.
Thank you so much. And which
Yeah.
grade are you in? Just curious.
Oh, I'm in 9th grade, freshman high school. Yeah.
Wow, that's very impressive. Okay, thank you so much.
Yeah, you're welcome. Bye, guys. See you next time.
Bye.
Bye.